With the lecture aspect, we're going to be studying sound waves today. So we're almost exclusively looking at sound waves except for the getting started portion. So sound waves are a kind of longitudinal wave. You should remember the longitudinal wave from yesterday. Those are the waves where the displacement of the particles is in the same direction as the velocity. So as I'm speaking, the velocity is going from my mouth to you, and air molecules are moving parallel to that direction. The way the air molecules are moving is a chain reaction. I have bursts of pressure. Air molecules hit other molecules. You have collisions, and it keeps the pressure moving. So you have to have, for a sound wave, a source. In the case of my body, it's the bursts of air coming through the little flaps in my vocal cords. If I clap my hands, it's the air quickly escaping from between my hands when I clap them. You have to have a source for the sound. Then you have to have a medium, something the sound travels through. One of the things that, as a physicist, I watch sci-fi movies, and you see them having a fight between two spaceships out in, quote, outer space. Outer space, which is much closer to a vacuum than anything that we can reach on Earth. And you hear the ship fire its whatever it's firing. And you laugh and laugh, I laugh and laugh and laugh, because you can't hear anything in space. Now, you can hear things that are inside your spacecraft because you have air there. But outside your spacecraft, there is no air. Something could be right beside your spacecraft. If it's not touching it, it makes a loud sound, you're not going to hear it because there's no medium in between. When we talk about light next semester, we'll talk about the medium for light and how this understanding of sound, that sound waves require a medium, led to some interesting misconceptions in light. Finally, we usually say that for sound, you have to have a third thing, a listener, an observer. Or you can go to the whole philosophy thing. If a tree falls in a forest and there's no one there to hear it, doesn't make a sound. How many people have heard that quasi-philosophical statement? Do you know what the purpose of that question is? It's a question about our perception of reality. Does something happen if it's not observed? It is really what's going on with that question. As a physicist, we have a certain worldview, and we say, if you have a medium and you have something that's going to cause the air to move, then yes, it makes a sound. I don't have to be there to observe it. But that is, you have other questions like, do we really exist? Are we just figments in somebody else's imagination? Yeah. That's something we in physics don't delve into. Typically, the physicist doesn't view that as a worthwhile thing to spend your time on. There are some that would disagree, including philosophers would disagree. When we talk about sound, we talk about a number of things. One aspect is the pitch. I can sing at a low pitch, at a high pitch, or anywhere in between. That pitch has to relate to something physical. It's not just your ear. And the pitch is the frequency of sound. So a low frequency is a low pitch, a high frequency is a high pitch. We don't have time this semester because of me falling behind to go into the theory of music, but just some basic things. You guys probably heard the term octave. Somebody asked me about it yesterday. Octave, of its very name, it tells you 8 somethings, right? An octave is 8 notes in a scale. It's actually 7, and then repeat the first one. But what's important about an octave in physics terms, if you go up an octave, you double the frequency. If you go down an octave, you cut the frequency in half. So going up 2 octaves, what have you done to the frequency? 2 times 2 is 4. So going up 2 octaves is 4 times the frequency. That's what an octave is. You have other things like a fifth or a third that we won't go into it all today. Won't even talk about the even-tempered scale. I love explaining all this stuff, but sorry. Next thing is the timbre, or quality of sound. With sound, if you have a pure tone, it sounds different than if you mix 2 tones. And so you can tell the difference in my voice and, let's say, Irving's voice because Irving and I have different timbres. We have a different set of frequencies that we produce even when we're saying the same thing. And so timbre is the quality of sound that has to do with the mixture of frequencies. And when we get to the lab part, I'll show you a little bit of how the frequencies mix. And then the last one, the volume, how loud the sound is. The volume is related to the amplitude of the sound wave. That is the displacement. So if you talk about a sound wave, you can either talk about pressure, how big the pressure is in the wave that's traveling, or displacement, how far from their equilibrium positions air molecules are displaced as the wave travels, because the air molecules go like this when the wave travels past them. So you can talk about either one, and the volume depends on the amplitude, how big the displacement is. Now, shifting right into the most important material for today's lab, superposition. Superposition is when you superpose or superimpose, either word works, two waves on top of each other. For low amplitude waves, such as the sound waves we're dealing with, the waves simply add up. So if I have two waves that pass through each other, I can simply say, okay, here's a picture of wave 1 at time 1. Should use a lowercase t there. And here's wave 2 at the same time 1. Well, I can just take wave 1 and add wave 2 and get what I'm going to see when I put them all together. When we were preparing stuff, I think Erica was in here, and we took one of the tuning forks that has two distinct frequencies, and we could see something that looks really close to what that resultant is of the two waves added to each other. And this is going to sound different than wave 1 or wave 2 because it's the two mixed together. Now, something you probably don't know, you would identify these as the same note. This one here is a pure tone. This one here would have a different tone, a different timbre, but you would identify them as the same note. So it's kind of like I can sing ah or e, same note, but different timbre because they have different additional waves on the big one. So with that superposition, we can have constructive interference. Here I have two waves that are exactly the same. So if I have two waves that are exactly the same at the same location, everywhere where one is positive, the other is positive, and it adds up to even bigger positive. Where one is negative, the other is negative, and adds up to even bigger negative. So the resultant, when you add these two waves together, is an even bigger wave, and we call that constructive interference. Constructive because it got bigger. Destructive interference, here they're exactly 180 degrees, quote, out of phase. The phase, you can think of the phase as just measuring in this picture you would measure it as the position, usually we think of it as the time, when you reach the peak. It doesn't have to be the peak, you just set your reference. Every time it gets there, you say, there's my start. If the other one gets there a little bit later, then they're out of phase. And the difference between when they reach the peak would be how much they're out of phase. And so here they're 180 degrees. 180 degrees is 1/2 a cycle, pi radians. All of those are same descriptors. It's that much out of phase. And because they're 180 degrees out of phase, when one is a positive maximum, the other one's a negative maximum. You add those up, it adds up to 0. And everywhere you look, the positive and the negative, it adds up to 0, so the resultant is flat. That's kind of surprising, but it's true. You can have two sound waves, and at some locations, you'll have no sound produced because you'll have destructive interference at that location. Other locations, you'll have even louder sound because you had constructive interference. Remember, waves are carrying energy. The energy can't be created or destroyed, but it can be distributed so you have more over here and less over there. Why is that important to today? because oftentimes we have sound reverberate, echo back. And so in our experiment today, we're going to be dealing with these tubes, and we'll have a sound wave that starts here, goes down to the bottom, and reflects back. So that means we'll have sound waves going both directions through the tubes. And so those sound waves will interfere. And when they interfere, we can have constructive or destructive interference depending on the waves. So here I have a picture showing two waves going opposite directions. And in the first one, let's just zoom this so we only see the first one. Well, it's as close as I can get. So we have them going opposite directions. And are they in phase, out of phase, somewhere in between? These are in phase. So if they're in phase, where one is positive, the other is positive, and adds up to being twice as high. When we have the two waves passing through and we have this constructive interference, it creates maximum displacements. Now we have these two. Would these be in phase, out of phase, or somewhere in between? These are out of phase. Or 180 degrees out of phase, or so on. And so here you have a positive and a negative. They add up to 0. No sound wave there. These are back in phase, out of phase, and so on. So this is showing that you could have in a region some places where it's in phase, some places where it's out of phase. Now to get to our fundamental of resonance. Let us take the example of this tube. This tube is open on both ends. If it's open on both ends, we call it an open tube. So an open tube is open on both ends. So just look at that tube. If we look at the pressure, what can you tell me about the pressure at an open end? It's the same as atmosphere. Very good. So at both ends, it has atmospheric pressure. Now, if I'm going to have sound going both directions, I'm going to have some places where the sound waves give you constructive interference, where the pressure is going to go high, low, high, low. Some places where we have destructive interference, where the pressure just stays constant. Which one is that? If the pressure is staying at atmospheric pressure. Is it going high, low, or staying constant? Constant. Now, we call something like this a standing wave. It's a standing wave not because the string doesn't move. The string, this is supposed to illustrate a string, would move up and down, but it's standing because you have the nodes and antinodes are the same place. A place where you have constructive interference is called an antinode. And where you have destructive is called a node. So if I'm going to set up a standing wave in this tube, my pressure has to be constant on both ends, so that's going to be a node. Now, I have the waves traveling both directions. I have places where I have constructive and destructive interference, nodes and antinodes. The pattern it gives me is going to be something that looks like this. Now, I have to make sure you know what this means because oftentimes we don't see it. Think about a wave on a string because waves on strings are much easier to visualize than the sound wave in that tube. If I have a string, here's my string unplucked. I pluck it, the two ends of the string can't move. When I pluck it, I'm going to make a wave that travels this way. It gets to the end, travels back. So I'm going to have waves traveling both directions. And I'm going to have the string doing something like this. And the two ends have to be fixed which means that I'm going to have at any moment, the string at the ends are stationary and it's moving up and down in between. So the string here will be going like this in the position I've drawn it. So a moment later, I might have the string perfectly flat a moment later. And then a moment after that, I'd have the string like this. So when we show the standing wave, we're showing the envelope of where the displacements might be. So here, the displacement could go anywhere from there to there. Here, it's a smaller. What do we call this location here? A node. And this one here is also a node. And this one here is also a node. What do we call the places halfway in between where we have constructive interference? Antinodes. The shape of this is still going to be the same wavelength as our normal wave. So what is the distance between a node and the next node? Let me see. Not the period, that's a time. Okay. The wavelength would be the distance to go there. That's the wavelength. So if that's the wavelength, what is this distance from node to node? It's half of that. And the symbol for wavelength is lambda. Why lambda, you might ask? This one I know. Lambda is the Greek L, length. Get it? So half a wavelength is the shortest distance between nodes. Now going back to our tube has to have a pressure node at each end. So it could resonate, setting up a standing wave like this, where the length of the tube is equal to 1/2 wavelength. But it could also resonate with a shorter wavelength, because this is not the only two nodes. It could go out to here. That's a full wavelength. So it's also possible that I could have L is equal to 2 times 1/2 wavelength. Or it could go out to the next one. It could be L equals 3 times 1/2 wavelength. So in general, we have a rule that for resonance to occur, for us to be able to set up a standing wave that has a node at both ends, the length of the tube must be an integer multiple of 1/2 wavelength. Now, I put L sub n, but you know what? Realistically, if you're playing a musical instrument, unless you're playing the old slide trombone, you don't just change the length of the tube. You set a length of the tube, and then the wavelength is chosen to match that. You disturb it with a range of frequencies, and only the one that resonates do you hear. So usually we solve this equation for lambda instead of L. That is, we write lambda sub n is equal to 2L over n. So those are the wavelengths that will resonate on a given length tube. So you could take a musical instrument, and I talked about this with Eric the other day. You can blow on it and go, playing it sounds nasty because this is not meant to be a horn. But if I was any good, I would be able to, you know what we normally do if we're no good? We overblow. I could go to a higher frequency, and I can make it play at a higher frequency. But it won't just play any frequency. I can't, right? I can't make it go continuously between them, because there's only certain wavelengths that will resonate on this tube. Now, I have to also point out that when I put my mouth on here, I change it from open to closed on one end. So this is going to behave with a different equation with my mouth on it. How could I have done this without putting, I could have blown over the top, but I can't make noise that way. I'm not very good. But it can only play certain wavelengths, hence only certain frequencies, because we know that there is a simple relationship. Frequency times wavelength is equal to speed of sound. So the frequency, put a subscript n, is equal to V over lambda subscript n. Substitute that wavelength we just did. Yeah. So these are the frequencies that an open tube will play. Now, I see that Rebecca brought her flute. A flute is an example of an open tube. A flute is clearly open on the end out there, and it has an opening over here that you blow over the top of. And so you're blowing over the top is going to cause fluctuations in pressure throughout, but it still opens the atmosphere, so it's open at both ends. So the notes that her flute plays are dictated by this equation. So if she changes the length of her instrument by opening holes, then she's going to change the frequency it will play at. And notice you do have the end there, so she can, by exciting it right with the same length, have 2 times, 3 times, 4 times the fundamental frequency. If n equals 1, we call it the fundamental. Fundamental. Anything above 1, we call it an overtone or a harmonic. So n equals 2 is the first overtone or the second harmonic. Isn't that lovely? So the n numbers the harmonic. It's the first overtone because it's the first one above. But it's the second harmonic because it's 2 times the original. So that's how a musical instrument like a flute or like a guitar selects frequencies. You don't have to pluck a guitar string in a special way to get it to resonate at one frequency. Now, does anyone here play guitar, like classical guitar? Yeah, I do know you play. Does anybody here record professionally? Yeah. I don't play guitar at all. You might do this, I don't know. I am told that sometimes you pluck the string in different locations to try to get a different timbre, different quality of sound. And the reason is, if you pluck, for instance, the very center of the guitar string, you're going to be exciting only the modes that don't have a node at the center. Right? If you pluck it at the center, there's no way to have a node at the center. And so you're only going to be exciting the odd harmonics if you pluck it at the center. And so it will sound different plucking at the center than it does if you pluck it, let's say, 1/3 of the way or 1/4 of the way. And so you actually can get different qualities of sound because you have different sets of frequencies depending on where you pluck it. Now that was an open tube. What we're going to do in lab today is a closed tube. We're still going to set up a standing wave. We're still going to have waves traveling back and forth through the tube, but it's going to be closed at one end. So if it's closed at one end, it looks like that. Now, where are you going to have a pressure equal to pressure atmosphere? Just at the open end. So here you'll have pressure equals pressure atmosphere. So that's going to be a pressure node. The other end has a wall. That wall can handle any pressure, assuming you don't break it, right? But we talk about sound waves in 2 ways. We talk about pressure, or we can talk about displacement. Displacement is the motion. What would you tell me about the limitations of the motion on the open end? well, going this direction, it's free to move in and out. What about on the closed end? It can't move into the wall. So here we have a displacement node. So we have a displacement node at the closed end. We have a pressure node at the open end. Now, I'm not going to go through any proof on this, but it turns out the displacement, the motion of the molecules, is out of phase with the pressure. When the pressure is at maximum, the displacement is zero. When the displacement is at zero, is at maximum, the pressure is at zero. So a pressure node is a displacement antinode, and a displacement node is a pressure antinode. So if we set up a standing wave now, at the closed end, I'm going to go back to pressure. At the closed end, we have to have a pressure antinode. At the open end, we have to have a pressure node. So now let's go back and look at our standing wave picture. What's the shortest distance between a node and an antinode? Here's a node. What's the shortest distance between a node and an antinode? 1/4 wavelength. The next one, going out to the next antinode, how many wavelengths is that? Not one. One would take us all the way out to here. It's 3/4. And if you keep going, the next one comes in 5/4 and so on. So for a closed tube, you have the length is equal, well, let's do it the same way that I did before. Yeah. Length could be 1/4 wavelength, or length could be 3 times 1/4 wavelength, or length could be 5 times 1/4 wavelength. In general, length is equal to n times 1/4 wavelength, where n is only odd numbers. Just as before, we usually solve this for the wavelengths that will resonate. So the wavelengths that will resonate is 4L over n. Use the frequency is equal to speed over wavelength is equal to speed over 4L over n. So we call this an odd function because it only plays odd multiples of the fundamental. Now, notice one thing. If I have this tube and it's open on both ends, the lowest frequency it could play was V over 2L. If I close it on one end, what happens to the lowest frequency it can resonate at? It's V over 4L, so it's 1/2 the frequency. Now, if I go from one harmonic to the next, I go up by V over 2L with the open tube. I go up by 2 times V over 4L for the closed tube, which turns out to be V over 2L. So the difference between the frequencies is the same, but the fundamental is halfway down if you close one end. How can you tell an open tube from a closed tube if you are given 2 adjacent frequencies? You just, with those 2 adjacent frequencies, you know that's V over 2L is the difference between the two. And so the difference between the 2 adjacent frequencies is V over 2L. If you subtract that down and you get to 0, then it has to be an open tube. If you subtract it down and you don't get to 0, you just go from positive 1/2 of that distance difference to negative 1/2. Then it had to have been a closed tube because the closed tubes are only quarter, 3/4. If you went down from a quarter, you'd be at minus a quarter. So we have different frequencies played by different instruments. Now, I'm going to come back after we have a break and talk more about this for the specific lab, but I do want to cover a little more on sound. I don't even have the computer running, so don't worry about getting any clickers. At the end of a guitar string, which tube was the guitar string like? An open tube or a closed tube? The guitar string was like an open tube because it had the same condition on both ends. An open tube has a pressure node on one end, pressure node on the other, because the pressure has to be atmospheric pressure at both ends. A guitar string is fixed in place at both ends, so it's at a displacement, no motion. What do we call when there's no motion? Node. So guitar string is at a displacement node at each end, which means the displacement must be 0 at each end. And I've already gone through that. Mathematically, it does say, but there. Mathematically, is the top one moving left or moving right? This goes back to what we talked about in class yesterday. It's actually moving left, but you gave an answer, and I appreciate that. How do I know if it's moving left or right? What's the difference between, well, there are two differences between these two equations. What are the two differences? Those negative signs. The one out front was really not important to my question. It is important to what happens when a wave reflects. If you have a wave that reflects off of a fixed boundary, it will be inverted, hence the minus sign. If it reflects off of an open boundary, it will come back the same, no minus sign. So this here is because it was reflecting off of a fixed boundary. This minus sign here is the one that had to do with the speed. We just take the speed is equal to the coefficient of time divided by the coefficient of position. The speed is omega over k. And if we have a positive sign, then it's going to the right. Nope, left. That's my left hand. I pointed that way and said right. Of course, if you look at me, you're like, well, it's your right. The minus sign means to the right. So we have these two waves that are going opposite directions. Here it's setting up a standing wave. This is showing the mathematics of how the standing wave occurs. You're adding the two sinusoids using the mathematical or trig relationship between two sinusoids. You have the sum of the two is this equation. It has one cosine omega t. That's a time dependent. So in time, at any location x, the displacement is going to be changing due to that first term. The second one, sine kx, that only has to do with position. And so if you find the x position where sine kx is 0, that's going to give you a node. So this here defines our spatial relation where we have the nodes and the antinodes. And then this here defines our temporal relationship, how it moves with time. And so as I pointed out before, at this antinode, it's going to be moving to different heights at different times. So this is just showing 3 different times what the heights are. And over a full period, it will have gone through that entire range. We already had that question. I am surprised I put it twice. Now this is going through work that we've already done. Has anyone here ever tried to tune a piano? You have? Really?
Yeah.
How did you do it? That's disappointing. Old school people did it differently. Okay, if we want to talk old school, let's talk when I was in high school. Before I was in high school, when they had band concerts, I loved to run out front and they had a little tuner. And I would whistle and try to get my whistle in tune. And how that thing worked was really smart. It has a spinning wheel. And on the wheel, you have different frequencies marked. And it has a sound sensor. And every time the sound wave hits a peak, it turns on the light. And so it's basically a strobe. And so the strobe light flashes at the same frequency that the sound wave is. And if you can make it so one of these bars is stationary, then you're on that note. So that is matching up the frequency of the spinning wheel to the frequency of the whistler. Now, we can have two sounds that are similar in pitch, but they're not quite in sync. If you weren't quite at the same frequency, you would see the lines slowly move. And so you need to adjust, taking my baritone up there and trying to tune it. I play my note, and if it's going this way, I'm like, okay, got to pull it out a little bit. If I pull it out a little bit, I'm increasing the length of my instrument, which means the wavelength that's going to resonate is a little bit longer, so I'm making it so my instrument goes a little bit lower in pitch, making it flatter by pulling it out. Push in the valve, makes a shorter distance, shorter wavelength, higher pitch. If you have two frequencies, like two sound sources that are not exactly in sync, then you have a cool effect that we call beats. Now, I'm going to ask Alex to see if he can find stuff for me, because I did pull this out, but now I feel I need to. Alex, come here. Across the hall. The room right beside room 130, it's like 120C or something. Like top left or top center on the wall there. The tuning forks that are on the wooden boxes. Okay, so I'm going to have him bring in something, hopefully, where I can illustrate the beats. But if you have two notes that are very close to the same pitch, but not exactly the same pitch, then at any location, you're going to have them very close to in phase for a while, and then slowly drift to being out of phase and then back to in phase. Well, if they're in phase, that means their peaks are at the same location and time. What are you going to hear when they're in phase? Well, will it be constructive or destructive or something else? It'll be constructive if they're in phase. So you'll hear it louder. If they're out of phase a little bit later, then you have destructive interference and it's going to be soft. And so you hear it loud, soft, loud, soft. The traditional way to tune a piano is you have a tuning fork playing its note. You pluck the string of the piano, and you listen for the beat frequency. You listen to how quickly it's going, yeah, 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 yeah. And if it's like a very slow frequency, well, it's going, yeah, 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 then you know you're close to the same pitch.
The room where?
I'll be back. Okay, here are my example for beats. Now, of course, I'm missing one thing. That is something to hit it with. These are tuning forks, but that's why I have him. You know that little mallet thing I have that has like half a soup ball on each end?
I can try to find it.
Yeah, try to find it. I'm not sure. Let's just do some show and tell while he's looking for this. Here's a whistle. The whistle has a plunger in it. And I'm sure it's perfectly clean, but I'll clean it with my spit just to make sure. What kind of tube is this whistle? Open or closed? Okay, I heard some of both. It's clearly open at this end. It has an opening right there for the whistle. So it's open at this end. Both open and closed tubes are open at one end. It's closed at both ends. Where's the sound going to come out? Yeah, it's not a very good instrument. The sound doesn't come out unless you have like a drum which has vibrating membrane. But the other end, what's the other end if it's got a plunger in here? The other end is closed. This is a closed tube. If I blow on it, what should happen when I make it longer? Right? Longer, lower pitch. It's like playing the old slide trombone or a slide cornet, if that's what you like. But less fun. Here's another fun, interesting little instrument. Everybody's played one of these, right? My wife, who knows nothing of physics, went and bought some of these for her grandkids. Let me tell you, they're a nuisance when you give them to the 8-year-old grandchild. How does this thing work? Okay, I swing it around in a circle and air blows across the end. The air blowing across the end, just like when I talked yesterday about the Karma vortex shedding and the Tacoma Narrows Bridge, it's going to make a turbulence that oscillates in time based on how fast the air is blowing. And so that's going to start pressure waves going down the tube. They get to the open end, they reflect back, and it is the basis of an instrument. So you go like this, and it plays a note. And if I go faster, but notice I can't play any old pitch. It's only specific ones, the ones that resonate. You know what? It's got a wooden handle that's about this long and it's really big. So this is another musical instrument. If I put my hand over the end and if I could swing it around, it would play lower pitch for the fundamental. But I can't do that, so I'm not going to try and look stupid. I look stupid enough as it is, right? I assume that was agreement. Now this here, what's the difference in these two? They both have a chamber underneath that we call a resonating chamber. If you play a guitar, and this time I'll definitely look at James. If you play your electric guitar and you don't connect it up to the amp, tell me about how much sound it makes.
Not very much, probably 15, 10 decibels at that.
Okay, 15, 10 decibels. That's very soft. When I was in college, the guy who lived next to me, he was kind of a slacker. He could have graduated a year early, but he just wanted to hang out with us. So he signed up for classes, didn't go to them. He stayed in his dorm room and played the guitar all day. But he was playing an electric guitar, so it didn't bother us because he didn't have the amp turned on. So if you play an acoustic guitar, instead of connecting to an amp and having magnetized strings and a magnetic pickup, you just have a hollow chamber underneath. That hollow chamber is acting like the tubes we've been talking about, except geometrically there's a lot of options for you to have resonance with that. So because you have a lot of options for that resonance, you have a lot of different frequencies it will resonate at, and it amplifies the sound. So that's what this is for. This is the sound box to amplify the sound through resonance. Otherwise, the tuning forks are the same, except one has putty on it. That putty is making it a little heavier, so it's going to vibrate a little bit slower. So these two will play almost the same note, but not exactly the same note. I'm guessing Alex still hasn't found it because he would punk me and be hiding back there with it. I'm hoping I didn't punk him and have it up here, which I'm pretty certain is not the case. So I'm going to try just banging it with this. See if I can make sound loud enough to hear. Okay. Non-excited, right? Just a nice pitch. The other one? Same thing. Now let's play both of them together. You hear it getting louder and softer, right? Now, because you have different frequencies, it doesn't take a lot of work to figure out how long it's going to take for them to get in phase and out of phase. And from that, we very quickly calculate the beat frequency is the absolute value of the difference between the two frequencies. So when I hit those, they're about 1 hertz. That's 1 cycle per second for the beat frequency. Hence, I know that they're about 1 hertz out of tune. That's really precise. You can tell within 1 hertz if they're the same pitch. Now, this has some very practical applications. Let's say you're flying a twin prop airplane. One of the things that would really be unpleasant would be if you cranked up one engine to, let's say, 1,500 RPM and the other one up to 1,200 RPM and you let off the brakes to take off. What would happen? If one is going faster than the other, what are you going to do? You're going to turn. You're not going to go straight. So you want to put both of the props at the same frequency. Well, all you have to do is listen. You throttle up one prop, then you throttle up the other, and you listen to the beat frequency. If you hear 2 separate frequencies, you know you're far away. When you get closer, you start hearing the beat frequencies, and then you just adjust the throttle so you don't hear the beat frequency anymore. It's just one frequency, and you know that they're right in sync with each other. You let off the brake, and you're going to be pulled straight forward. So that's a really good practical application of using these beat frequencies. A really annoying application of these beat frequencies is the radar gun they use to charge you money for driving down the road. Because they shoot out a wave, it hits your car and bounces back, and when it hits your car and bounces back, the frequency shifts, what we call a Doppler shift, which I'm not going to have time to talk about. But the frequency shifts, and the shift is dependent on how fast you're going. And so they mix the two together, see what the frequency difference is, and they calculate how fast you're going. And then they give you tickets if you're going, above the speed limit, which you shouldn't do, right? And none of us would ever do that. Yeah. Here's a good question that you can just blurt out the answer. What type of wave is a sound wave? Did I hear sine wave? Which one of these? Okay, maybe we couldn't all blurt it out. Transverse? It is not a transverse. Transverse waves, it travels like this and has displacement like that. It's a longitudinal wave. Latitudinal doesn't exist, neither does sideways. And Rayleigh and Love waves are combinations of longitudinal transverse waves that occur at surface boundaries. So sound wave is a longitudinal wave. I talked about beats. You can also have that occur in space. If I have 2 sound sources that are in phase, that is, each of these sound sources is sending out its highest pressure at the same instant, there will be some locations where you have constructive interference, others where you have destructive interference. Well, that's constructive. Others where you have destructive interference, somewhere like here would be destructive. And so you're going to have locations where it's loud and where it's soft. Where is that important? It's important in my TV room. In my TV room, I have speakers set up, and my sound system's, of course, sending out sound waves. And I want to make sure that I have constructive interference there in the seat where I'm sitting. And hopefully it's close to that on either side where my son and my wife sit. This is used by sound engineers to actually help you to have the full experience when you're watching TV. If you have just one speaker, of course, this doesn't come into play. But if you have 2 speakers, as shown here, they can do tricks to make it sound like the sound is coming from different locations. As an example, if they have the sound coming in phase from both speakers, it's going to sound like you're hearing something directly in front of you. If it's exactly out of phase, you're in the place where it's going to be an antinode, and it's going to sound to you like the sound is coming from all around instead of from a specific location. And so they do this. The sound engineers do this to help enhance the experience. And of course, that's why we have things like surround sound, more speakers, more control of where it sounds like things come from. And okay, this one is an important one. Intensity is power per area. If I have a sound source like this thing, as the sound comes out, the power, that is the energy per time traveling through space, is constant, but the area that it's going through is getting larger. The area is getting large as the surface of a sphere, 4 pi r squared. So the intensity, the power per unit area, is dropping inverse square to the distance away. So that means the intensity, okay, so I'm going to get really close here. I'm about a meter away from Irving. And I'm about 8 meters away from Trace. So if Trace is 8 meters away and Irving's 1 meter away, how does the intensity that Trace is hearing compare to the intensity that Irving hears? What? Okay, Irving has more. By what factor? 64, because it's 8 times difference in distance, and it goes as 1 over distance squared. So 1 over 8 squared is 1 over 64. So Trace is only hearing 1/64th the intensity that Irving hears. Now we tend to think, wow, he's hearing just a fraction, 1/3 roughly, not 1/3, well, he's hearing just a fraction of what Irving's hearing. Does that mean Trace has a hard time hearing it? No, it's not that hard. It's not. One reason is because I use my teacher voice and I project, so I speak loudly. But another is because our hearing is not linear. We don't perceive sound linearly. As the sound drops off, our perception of how much it got soft is a smaller change. So now we're going to switch to us hearing sound. Our ears are pretty miraculous devices that God created, I believe, that have a range that we can perceive somewhere between 20 hertz, that is 20 cycles per second for the lowest sound we can hear, up to about 20,000 hertz, 20 kilohertz, the highest pitch that we can hear. As we get old, that highest pitch drops, so I probably can't hear as high a pitch as you guys can. We have excellent hearing that's most sensitive somewhere in the range of about 1,000 hertz. In fact, here's a graph that shows how well you hear for a typical person. A typical person hears the best in this range right here. These lines are marked in what are called phones. Phones are, it sounds like the same loudness at all frequencies on that line. So that means the place where it's the lowest means the lowest actual, the vertical axis is a logarithmic axis proportional to the intensity. So the lowest intensity sounds the same loudness as a much higher intensity on either side. So 0 phones is the threshold for hearing. You can hear the lowest intensity at somewhere there, that's somewhere around, let's say, 4,000 hertz. And you don't hear nearly as well at high frequencies or low frequencies. So phones are set to be equal sound. The phone scale is actually calibrated so that I think it's the 70. Is that right? Yeah. I think it's so the 70 phones at whatever frequency I circled is 70 decibels. The calibration is something like that. So we have the decibels. You've all heard of decibels, right? In fact, James used decibels a few minutes ago. But what we don't know so much is, what is a decibel? I noticed I should have pointed out this range here. When you're talking, this is the general range of frequencies and intensities that you talk. So you see, we generally speak somewhere around 60 decibels. Now, when I'm here teaching, I'm somewhere closer to 80 decibels, which is a fair amount louder than a normal conversation. Okay, and notice the range of the human voice and frequencies. in the range that we hear roughly the best. The range of the frequencies we usually speak at, where we hear very well. Okay, so let's get to, well, first of all, hearing problems. This is essentially what my hearing's like. I went and had it checked a few years ago because I just wasn't hearing students as well as I should. I expected it to look like the bottom graph. The bottom graph is typical of people who are old. They lost flexibility in the little fibers that vibrate in the ears, and so they don't hear high pitches well at all. That's what I thought it would be like. It turns out my hearing is like this. I basically am just missing this area of hearing, probably because I mowed my lawn without a muffler on the lawnmower for like a decade. It was just really loud, and I was like, it's kind of like going to a rock concert and, you know, standing next to that speaker saying, yeah, groovy, dude, or whatever people say these days. You know, it damages your hearing. Okay, no biology, just don't have time for this. This is going through the ear and all of the mechanisms. I do want to point out just a couple things. The pinna, the outer ear, has as its primary job collecting sound waves, guiding them into the ear. So those of us with bigger ears have an advantage. We're collecting more sound. Then we have the ear canal that channels it in. And then we have the eardrum with its stirrup and anvil. The stirrup and anvil is a mechanical machine device that increases the motion, so it's a kind of amplifier. And then it drives air down, through this channel that has little cilia that vibrate, and you have different frequencies they'll vibrate it. And so what, you know, depending on where you are, it's different frequencies they'll vibrate. So you determine the pitch by which ones of those are vibrating. It's really an amazing system. What frequency do we hear the best? About 4,000. Very good. What range do we speak? Somewhere around, 200 to around 2,000 hertz, 2,000 or 4,000 hertz, somewhere in that range. So we're speaking in a range that we hear really well. We would hear a little better if we spoke in really high voices, you know, at the top end of our range. Okay, so the last thing for today is going to be talking about these decibels. We set a kind of arbitrary threshold of hearing intensity of 10 to the minus 12 watts per meter squared. Remember, intensity is power per area. So it's kind of arbitrary, 10 to the minus 12 watts per meter squared. And so any other intensity is going to be louder than that if we can hear it, right? But we can hear a huge range of intensities. We can hear intensities ranging from 10 to the minus 12 watts per meter squared up to rupture of the eardrum. You can hear all the way up to then. Well, what intensity is going to cause the eardrum to rupture? For the purposes of physics, we say 1 watt per meter squared. Now, you're going to hear 1 watt per meter squared, and you won't have a ruptured eardrum, and you'll say, my physics teacher was wrong. Well, it's a number we use. It's where you start running into potential for having damage done. But you notice that's a million, otherwise known as a trillion? No, million, billion, trillion, yeah, trillion. Otherwise known as a trillion orders of magnitude difference between the minimum intensity you can hear and where it becomes painful and potentially dangerous. We have a huge range that we can hear of intensities, and nobody wants to talk about that huge range. So we take a logarithmic measurement to make it so the numbers are smaller. And so we define the bell as 1 bell is equal to the log of intensity over intensity oct. That's the definition of a bell. But nobody ever says bells. What do they say? Decibels. So a decibel is a tenth of that. Hence,
1 decibel, dB is what we use for the symbol, is equal to 10 log of intensity over intensity threshold. So now we can take what James said, somewhere around 10 to 15 decibels, right? So let's just say 10 decibels to make it easy. So with what James said, he said the guitar plays at about 10 decibels if you don't have the amp on. So that means, by the way, beta is the symbol we use for the sound intensity level. Sound intensity level. Come on. Well, we can immediately determine the intensity that his guitar is playing. First, let's just move the 10 over. Beta over 10 is equal to log of I over I0. How do you get rid of a log mathematically? Log is the inverse of 10 raised to a power. So if I take both sides and put 10 raised to this equals 10 raised to this, 10 raised to the log of I over I0 is by definition I over I0. And so that means I is equal to I0 times 10 raised to the beta over 10. So in the case that was given to us by James, that would be 10 to the minus 12 watts per meter squared, because that's what I0 is, multiplied by 10 raised to the 10 over 10. Well, 10 over 10 is 1. 10 raised to the 1 is 10. And so that's going to be 10 to the minus 11 watts per meter squared is the intensity that he gets from his guitar when not connected to the amplifier. Now, okay, is his number actually right? I don't know. I don't care. It probably is a little higher, but it doesn't matter for our purposes. So we can use this decibel to understand the sound. Now back to how loud it sounds. We said that for trace, the sound is about 1/64th as loud as it is for Irving. And so we could say, if Irving hears, let's say 80 decibels, how loud does trace hear? How would I do something like that? Do what? One decibel.
Or what is 1 decibel equals the log of intensity? When you do the same thing.
Okay. The general way that a student would approach this is to say, I know beta Irving is equal to 10 log of intensity Irving over intensity for the threshold of hearing. And I know that that's not the color I want at all. That beta for trace is equal to 10 log of intensity trace over intensity 0. So I have those two relations, and I can use what we said, that intensity for trace is equal to intensity for Irving divided by 64. Now, here's the beauty of this calculation. Most people in your shoes would take the upper equation and solve it for intensity Irving, and then put that in the lower equation and get the beta for trace. But with these logs, you can use the power of logs to make it a simpler calculation. Because with logs, log of A times B is equal to log of A plus log of B. So I can take this equation, that's 10 log of intensity of Irving over intensity 0 plus 10 log of 1 over 64. Well, we know beta Irving is this first term. So that's equal to 80 decibels plus 10 log of 1 over 64. So all I got to do is put in my calculator, what's the log of 1 over 64? Irving, since he's my example.
-1.8.
Okay, so it's negative 1.8. I have to multiply by the 10 out front, so minus 18 decibels is equal to 62 decibels. So what Trace is hearing is about 62 decibels if what Irving's hearing is 80 decibels. 62 decibels is similar to a conversation in how loud it is. For Irving, it's much louder because he's up close. And it may not be that comfortable as being in the front row because it's much louder. Final couple things. And no, we're not going to do that. We're not going to do that. Okay, I don't have slides for them. How much does our sense of sound vary? We say that if intensity prime is equal to 10 times intensity that we start with, it sounds about 2 times louder. So you go 10 times the intensity, it sounds about 2 times louder. Now, if we go to our decibel equation, so there I put in my intensity prime is 10i. That's going to be 10 log of 10 plus 10 log of I over I0. That's the original beta. And so the beta prime is the original beta plus 10 log 10. By the definition of log 10 is saying, what power do I have to raise 10 to get 10? Because it's a base 10, what power do I have to raise 10 to get that number 10? Well, clearly 10 raised to the 1 is 10. So log base 10 of 10 is 1. 1 times 10 is 10. So it's 10 decibels. Oh boy, I'm on not on the same line even. So for something to sound twice as loud, it has to be 10 times the intensity or 10 decibels louder. So what would sound twice as loud as the guitar playing at 10 decibels? How many decibels would sound twice as loud? 20. And how many decibels would sound twice as loud as 20 decibels? 30. Right? You just go up by 10 to make it sound twice as loud in the decibel scale.